Recording in progress.
So we will start very soon now. Just a message to all speakers of this session. I will give you 5 minutes warnings before the end of your presentation. So every talk is scheduled for 20 minutes. So I give you a warning after 15 minutes so that we stay in time with the whole session. And since it is 2 p.m. In Europe,
7 in the morning in Texas.
And it's early morning in Texas. Hope you had breakfast already. And so let's get started. So I welcome everybody here in the session. My name is Ralf Rülsberger. I'm currently at the University of Jena in Germany. So where it is 2 p.m. now. And it's a pleasure actually to share this session. We have 5 speakers with various subjects. And our first speaker is Effi Shamoun from the Weizmann Institute of Science in Israel. And yeah, the stage is yours. Please go ahead.
All right. Thanks a lot, Ralph. And thank you, Olga, for the opportunity. So I'm Effi Shamoun from Weizmann Institute. I want to talk about quantum interfaces between light and matter. So basically, if you want to do quantum science with atoms and photons, you would want them to strongly interact. Because if atoms and photons interact strongly, then you can have entanglement, and then you can have all sorts of quantum tasks like memories, gates, or just to study many-body physics with atoms or photons. So we need strong interactions, and we need to characterize it. So imagine you have this atomic, so you see my mouse, maybe I should switch, okay, too late. So there is this atomic system and there is a target mode of light. This is the, let's say the light mode that we can launch and we can detect. And then we can describe 2 kinds of emission rates, the one to the target mode and the one to all of the rest of the modes. And then cooperativity, we can call it, will be the ratio between the emission rate to the direction we like and the direction we don't like. You can also rearrange it as the emission to the direction you like divided by the total emission. Then you can call it the efficiency, and I will call it the reflectivity for a reason you're going to see soon. Now you can ask, if I have one atom in free space and I shine a Gaussian beam with some cross-section A, what will be this cooperativity? Well, it will scale like the cross-section of the atom, which is lambda squared, the transition wavelength, divided by A, and then if we take, let's say, here 800 nanometers and A is 10 microns, then you don't get too far. So usually this is why one atom will not couple well to light. And then you need to fix it. The way you fix it, you look at this cooperativity. You cannot fight, in many cases, you cannot fight the emission, the undesired one, but maybe you can enhance the emission to the desired direction, and that's what we usually do. We go for the numerator. So in cavity QED, you just enhance it by a finesse, the mode that you like. With atomic ensembles, you build constructive interference using optical depth, and then basically you increase by the number of atoms. In waveguide QED, you just make the cross-section of this desired target mode smaller. But all of these things, they don't fight the gamma scattering, the scattering to the direction that you don't like, the losses. Now, a different paradigm that we're kind of working on, that came in the recent years, is to talk about something like atomic arrays. So in this system, you have one layer, let's say, of dozens of atoms. And there are no dielectric structures, no waveguides, no cavities to help you confine the light, and no million atoms like in an atomic cloud. So the emission to the direction that you like, the numerator here, the cooperativity, does not change much. But the interesting thing is that because the atoms emit collectively, and you can arrange them in some way, maybe you have a chance with interferences to reduce the denominator. So it's really the opposite approach. of how to still get this cooperativity larger. And again, the resource here is not many atoms or not bulk dielectrics. It's just really this collective physics. So give you one word about the collective physics. So if you have a bunch of atoms and they're far from each other, each one of them will emit to some random direction with some decay rate gamma, and it has some transition wavelength, frequency omega atom. But if the atoms are close enough, you can imagine that the photon emitted by one atom hits the other atom, and then you have all of this multiple scattering, and each scattering will be weaker if the atoms are far, but if they're close, this is a non-perturbative thing. So either you call it multiple scattering, or you look at the atoms and you think of it as dipole-dipole interaction. The atoms exchange interaction via the exchange excitation via the photon. It doesn't matter. It's the same thing, and there's this interaction kernel DNM. Now, if I take a two-dimensional array, I have to diagonalize this dipole-dipole interaction matrix to understand what's really happening here. What are these normal modes of the system? It's not individual atoms anymore. If the array is infinite and ordered, then it's kind of easy to see that in a 2D array, let's say, you'll have these Fourier modes on the lattice or Bloch modes, whatever you like to call it, and I call it collective dipole modes that are characterized by some wave number, these surface modes. And each one of them has a frequency which is shifted from the original frequency, and a width which is also different, and it all comes from this dipole-dipole interaction. And the interesting thing is how it's coupled to light. If you shine light with in-plane momentum, K, then you're going to excite the same dipole mode K, just because of discrete translation invariance. So, it's kind of simple. You just diagonalize the problem. And now you can think of a scattering problem. So imagine I shine light with some normal, with some in-plane momentum K. Because of this momentum conservation, I'm going to scatter light only to these directions, either forward or backward, with a scattering amplitude R. Now, if I shine the light exactly on resonance, not with the original atomic frequency, but with this collective frequency that we found of the mode surface mode K, then in theory, I'm going to get perfect reflection. Okay? The light comes through, the -1 here will cancel the 1 here, nothing comes through, and everything is reflected. This is numerics for a finite Gaussian beam. The theory is analytical for infinite arrays. Everything is working and nice. Numerics also, and even experiment. So the experiment, you take a 2D optical lattice. This is in MPQ, Emmanuel Bloch's group. And if the atoms are disordered, you get few percent reflection, even less than this 7% actually. And when the atoms are ordered in the 2D optical lattice, you get 60%. Why 60 and not 100? There are many imperfections. It depends how good is your system. But the bottom line is that it's not 100%. And I did not manage to reduce this gamma loss to 0. Okay? But it is reduced. Okay? So basically, I still have something like cooperativity. I reduced considerably the gamma loss, and the gamma to the direction I like is something around the same order of magnitude. Bottom line, atom array, single layer, is a very good reflector. And it means the cooperativity is very good. So it's really reflection that I measure, okay? It's really this thing that characterizes everything, the strength of coupling. And it's not that really I care about reflectivity. What I care about is strong atom-photon interaction, which here is characterized by reflectivity, okay? So once you understand this, you understand you have a novel atom-photon interface, which is entirely based on collectivity. And then you can have many works and many things that people have done, including us, on how to use it for quantum memory, for quantum nonlinear optics, and other ideas. But really today I want to concentrate on the new work that we have, which is really to understand why reflectivity characterizes everything here, and what kind of atom-photon interface this is. So we try to really understand this. So imagine the following generic 1D model of light-matter interaction. I have some collective dipole of bunch of atoms, and I have my preferred mode. And there is emission rate to the mode. This is the collective atomic dipole. Let's say I diagonalize the dipole-dipole interaction kernel. And there is this target mode. And there is emission to the target mode and emission to the other directions. In the infinite atom array, this P was just this Fourier mode. And this E was the corresponding field in the same direction. Okay. Now I can write equations of motion for this generic model. We write Heisenberg-Langevin equation, doesn't matter. These equations just have two parameters in them, emission to the direction I like and emission to the direction I don't like. Never mind what you do here with the math. Everything will be characterized by these numbers. Okay? So basically, everything will be characterized by a cooperativity, or if you like, reflectivity. Okay? Why reflectivity? Physical intuition. If I have a 1D scattering problem, what on earth can happen? You know, reflection just means you absorbed and re-emitted. So I can classically take this model and calculate, if I shine light, what is the fraction that is absorbed? I'll just get this number, cooperativity divided by 1 plus cooperativity. I can also take a dipole excited and see how much light was emitted to the 1D direction versus to the direction I don't like, and I'll get the same number. When I multiply them, I get reflectivity. So that's it. Everything that, if light wants to talk to atoms in a 1D model, that's the only thing that can happen. Reflectivity will characterize everything. For example, you can take this model, this 1D model, and add another level, which is a stable level, and do a quantum memory. Never mind the details now. Quantum memory, the protocol, is exactly like reflection. Just you break reflection into 2 steps in time. When you store the excitation in the atoms, this is the absorption. When you retrieve the excitation, it's the emission. And you run the protocol of quantum memory that you can find in many quantum optics papers, and you know, no surprise, you'll just get the reflectivity. The efficiency of a quantum memory is the reflectivity if you happen to be in a 1D model. Now, we also did the same we did protocols for quantum nonlinear optics, for entanglement between photons within this variance of this 1D model. And no surprise, the classical reflectivity is the number that determines everything. So this is the efficiency of quantum tests. All right, so this is great. If the world was 1D, we were in good shape. But now, this leads to our approach of how to think of atom-photon interfaces for arrays and even beyond array. So imagine you take now this 3D problem, many atoms, many photon modes. It's a finite size system, not infinite anymore. Very difficult problem, complicated problem. And I wish I could map it to the 1D problem. If I could map it, I would characterize everything with 2 numbers, gamma and gamma loss. So I take equations of motion of many atoms and many modes, and I somehow shape them and find what is the relevant collective dipole mode and what is the relevant photon mode that couples to it, such that these equations, complicated one, will degenerate to this equation. And once I have this equation, I'm done. I have my cooperativity, I have my reflectivity, and then I can run all of my protocols, calculate them in the 1D model. I don't have to do it again and again and again in this complicated calculation. Now, how to do this? Just to give you a hint. So basically, I have equations of atom N coupled to all of the atoms M with a dipole-dipole interaction kernel D and M. From this picture, you might remember. How on earth will I get to this? Well, one method will be the following. I will diagonalize this matrix D and M, which is depending on the positions of the atoms and how the Green's function of photons look like, which is the dipole-dipole interaction. I will find the mode, the eigenmode, which is the most paraxial. Why? Because I want to couple it to light, which is paraxial, because we want to shine paraxial light. And I just find this, I find all of the eigenvectors of this dipole-dipole matrix. One of them will be paraxial, hopefully. From the eigenvalue of this eigenvector, I will identify what is the total emission. From the coupling to the light mode that I will define, I will find what is the good part of the emission, and I'm done. Everything is done, okay? So just to show you an example. Easiest example is the following. I take a 2D array, which is finite and also has random positions, some disorder in it. And this is a hard problem, realistic problem. Here I'll show you how I diagonalize the problem in an approximate way. Naturally, I would love to shine a Gaussian because it's nice. Now, a Gaussian beam does not really diagonalize it, but it approximately diagonalizes, because a Gaussian beam, if it's paraxial enough, is almost like the Fourier mode of normal incidence. Now, this is a finite size array with disorder, but I can still reshape the problem. And I'll find what is my collective dipole, what is my collective beam, and I'll find what are the emission to the direction I like, which is basically the emission of the infinite array times some fraction of how much of the Gaussian beam really hits the atoms. The Gaussian beam can be larger than the atom array. This is why you have an error function. This is how a Gaussian is fitted to a square. So this is the emission rate to the direction I like, is the emission rate of an infinite array times this error function. The loss is everything which is 1 minus this, plus everything that comes from this order. And we actually managed to calculate it analytically. We find what is the losses from here, and this order, we have some perturbation theory. We found what is the scaling of the losses with the lambda parameter, never mind. And we even can verify it. So we have analytical expressions. On the other hand, this is really easy. You take this problem of scattering in a classical computer. We shine reflectivity from a bunch of atoms. We calculate reflectivity from a bunch of atoms. Reflectivity. To calculate cooperativity is hard. You have to calculate how much power was emitted to all of the world versus to the... We only calculate reflectivity, and we compare it to our analytical theory, and you see that the numerics fits the analytics. So this is just to show you that we managed to approximately diagnose the problem and identify a 1D model. And once we have the reflectivity that can be calculated classically or measured in experiments, we have all of the quantum efficiencies for quantum tests. Now something even cooler. Different example. Imagine now that I have a 2D atom array, which is finite size, but now I have filling fraction, which is not 100%.
Questions.
Pardon. Yeah, okay. So I have a filling fraction, which is not 100%. This is what I show you here, 85% filling fraction. And now I really go by the protocol I showed you. I diagonalize the matrix of the dipole-dipole given the positions of the atoms. I find the mode, which I find this mode. This is one of the eigenmodes. You see the atom, this is an eigenmode that you have a spot here and a bit of a spot here. This is going to be my collective spin eigenmode. Now I smoothen it, I do interpolation to define a continuous mode profile that I'm going to shine. Now to show you it's paradoxal, I'm going to do the Fourier transform, and you see that in Fourier domain, it's really narrow. Now I shine this mode of light on this atom array, and I will excite this collective mode. And indeed, we see by numerics, just by numerical calculation, we see 99% reflection, and the theory, which is given all by these eigenvalues, is 99 also. So it's a bit, and you can also get the decay rate, the shift, everything. That's one example. Now you can compare, let's say I shine a Gaussian beam, the best Gaussian beam, and I keep reducing the filling fraction. The Gaussian beam will fail more and more with reflectivity, getting to 70%. If you run our protocol, you find the eigenvalue, you shine the eigenvalue all the time, we stay on something like 95%. So you can have 70% filling fraction, which is not even a Mott insulator. You can really load them maybe randomly with some tricks, and you can get 95% reflection without having the Mott insulator or anything like that. So that's kind of cool to show you the power of this method. Another way, not even an atom array, just a circular, we take a circular array. What are the eigenmodes of a circular array? Who knows? I just calculate, look at this eigenmode. It's spread all over the place, but it's pretty paradoxical. So we, again, interpolate to find a continuous wave to shine. It's still paradoxical. We shine it, we get 96% reflection. Okay, and there are other modes. If we take 3D arrays, if you put them in a Bragg condition, we have the same theory, and we just show that all of our cooperativity is enhanced by the number of layers, which is something, it's like optical depth, something you would expect. Okay, let me conclude. So I show that atom arrays, or even beyond atom arrays, are novel atom-photon interfaces. They're entirely based on the physics of collective light-matter interactions. We show the universal approach where we can map problems to 1D problems, and therefore reflectivity that you can actually measure will characterize efficiency of any quantum task, almost any. We went beyond simple arrays like the filling fraction or circular stuff, and this is real stuff. We have experiments. So I want to thank my students, Yaakov Solomon and Ronnie Ben Maimon from the Weizmann, and also the early collaboration with Susanna Yelin, Misha Lukin, and Dominic Wild from Harvard, and also the experimentalists at the Weizmann, which are building Twizzler arrays, and we work with them on that, which is Nir Davidson and Ofer Fürstenberg. Thank you so much.
Okay, yeah, thank you, Efi, for this very interesting talk about a novel atom-photon interface or platform, how you want to call it. So are there questions? So please use the raise hand functionality of Zoom to indicate that you have a question so that I can see it. Igor Pikovsky. Hi, Igor. You have a question.
Yes, that's right. Hi, Effie. Thank you. Very super exciting. Can I ask you? Sorry, maybe I missed it, but does this work now for, like you say, for different filling fractions? So does it work arbitrarily? So if you like just randomly fill some array and you have a lot of errors, or is it already very specific profiles?
Okay, so we eventually want to shine light, which is paraxial. So look at this protocol here. We wish that you can always find eigenmodes, no problem, but are the eigenmodes paraxial if you move them to fair plane? Because we want to shine paraxial light. If you take a random, so if the modes are paraxial, it means that in real space they have to be non-localized. I'm not sure about theory like Anderson localization and stuff, but I mean, if you just take random, I'm not sure you can always, in most chances, we didn't find any paraxial mode. Now, can we do the theory beyond paraxial? I think we could, but we concentrated on the practical problem of we would love our beams that we shine to be paraxial, because then you can design them with an SLM. You can design any shape you like. That was the motivation.
Right. So, sorry, if I can specify only 1 second. Yeah, no, I completely agree. A good answer. I just mean, is there a way to somehow find like, an optimal or best case paraxial approximation to this kind of non-paraxial case? So somehow like a distance, like a state distance, or so, find the closest paraxial beam that would work or something like that.
Yeah, well, I mean, there is a heuristic approach. You take a Gaussian and you say that you can play with the waist, and then you optimize the waist. But you'll get 50% reflection from something random. You wouldn't get too much.
Okay, are there further questions? There's one. Olga has one.
Well, if you could say a couple of words about experiments, what kind of system?
So the experiment that was done, and there are already 2 experiments in the same group, is really 2D optical. So there is the optical gas microscope, which is basically a 2D multi-insulator. Okay, so you can imagine now if it's ordered, here you have the distance between the atoms is something like 630 nanometers, if I remember correctly. This is the lattice spacing. So imagine 2D lattice with lattice spacing of less than a wavelength. This is rubidium atoms, okay? The filling fraction was 90-something% because it's a multi-insulator. And now you shine light, and you see that you have reflection of 60%, say, okay? Because you hit the atoms, because of anti-trapping, because of many issues that could be solved if you wanted to optimize. Now, you take the same number of atoms, same density, and you disorder them on a 2D pancake. And you shine the light, and you see much less reflectivity, okay? Dramatically less. You come on resonance, and still you don't see much. Because it's just, and the number of atoms here was 200 atoms, okay? Something like 200 atoms.
Okay, good. Thank you.
Okay, I think we have to move on, actually. So let's thank Effie for this presentation again. And we have the next speaker. It's Vitaly Kokorovsky.
Vladimir.
Sorry? Vladimir, sorry. Sorry.
It's okay. We are twins.
Now I have the full name. I have here on the program. There's only the initials. And okay, good. Yeah, Vladimir. So
do you see my presentation?
So your presentation, you can go in full screen mode. Then it would be even better. And
let me see.
So we have a presentation about asymmetric superradiant lasing in a asymmetric Fabry-Perot cavity. So
let me find how to include the full screen mode.
On the bottom right, there's a little symbol where there's a, yeah. Do you see that?
Как бокал внизу.
Наверху пока слайдов.
Наверху.
So right left of the 87% indication, whatever that means, there's this symbol.
Показ слайдов.
That's the
I don't
on the
see
right,
the
on the
full.
bottom right, on the bottom right.
It's okay. We can do it like that.
Or we do it like this.
Just move from the top, from files, then move several, and then go to the slideshow. Показ слайдов. Slideshow. No. Above.
Above.
Slightly above. Above. Oh, okay. Then go to the right. To the right. Stop. Here. Then
Here.
to the left. From the, from the beginning.
From the beginning. Okay.
That's it.
And
Okay.
now,
Okay.
do you see now?
Yes. Mm-hmm.
Unfortunately, I don't see myself.
Oh.
Is it the case now?
Yeah, we can see your.
Sorry for this interruption. So my talk is devoted to quite simple in formulation, but not very simple in solving a problem. I'd like to present an analytical solution for the steady state, strongly asymmetric superradiant lasing in a slightly asymmetric Fabry-Pérot cavity. Namely, we find an exact solution of the Maxwell-Bloch equation in a dense extended ensemble of active centers located in a local slightly asymmetric Fabry-Pérot cavity under the CW non-resonant pump. The solution takes into account a strongly asymmetric self-consistent half-wavelength population inversion gradient, which is formed by the self-generated homogeneous counter-propagating waves. The solution is valid for any kind of any classes of lasers, A, B, C, D, and so for our surprise, this problem has not been solved yet. It's valuable in any case of open Fabry cavity when with different mirrors, not very perfect, when the finite value of transmissions are taken into account. Namely, we need very dense active medium to ensure very high amplification factor by many times. And also, we need a long relaxation time of polarization. That's the time, a lifetime of phase lifetime of phase relaxation of optical dipole oscillations should be high enough compared to the photon lifetime in a cavity. In this case, the solution is very non-trivial, and even in a slightly asymmetric cavity, we will have strongly asymmetric lasing. Let me omit examples. I only should say that in addition to authors of this talk, Yekaterina Kacharovskaya and me, all analysis and all investigations of superradiant lasing was made in collaboration with my twin brother, Vitaly Kacharovsky. So let me remind that we have 4 classes of lasers, and they differ by different relations between relaxation rates of the field in the cavity, the inversion, population inversion of the active medium, and the polarization of the active medium. In the case of our interest, when the polarization decays more slowly than the field, there appears very pronounced interaction between counter-propagating waves, which produce population inversion gradient, half-wavelength gradient. And this is typical for the superradiant lasers. This class D lasers was introduced in our works, and later on it appears in reviews and become available in some textbooks, for example, in the textbooks by Hanin and Arecki and Harrison, devoted to different classes of lasers. But let me skip this discussion, and because the solutions I would like to present is valid for any kind of lasers, only also for standard lasers. You see a typical scheme of a laser. For example, it may be a many-layer active region in heterolaser, and edge-emitting heterolaser, and with different mirrors. Right mirrors are 2, and the left mirror are 1, and we will assume that the left mirror is slightly better than the right one. The necessary condition of formation of strongly high wavelength grating and hence strongly asymmetric superradiant state is written here, and we need the pumping and the laser length are quite high, so that we should be far above the laser threshold. The condition is involves the so-called cooperative frequency, which is mainly defined by the atomic density and the matrix element of the pole transition, lasing the transitions. And we will use dimensionless variables, so we will measure time and length in this, multiplying them by this cooperative frequency and by cooperative length. The statement is that under this condition, the actual self-consistent asymmetric lasing parameter of asymmetry of lasing are small here, which is the ratio of the output intensity from the right mirror to the left mirror, and this factor of asymmetry of lasing may be much higher than that factor calculated without taking into account this half wavelength grating. This is which was ratio for asymmetric laser mode without taking into account inhomogeneity of the population inversion inside the laser. So, in fact, you know, there are a lot of examples of superfluorescence, and in any case of, if we will have continuous wave pumping, we will observe in this kind of lasers this structure which I am going to describe. So, in one-dimensional laser, in the two-level approximation, for if the laser length is much greater than the wavelength, we can introduce the amplitudes of counter-propagating waves, electromagnetic of the electromagnetic field, and of the polarization, and also divide the population inversion in two parts: slow varying in time n, and the half wavelength gradient with the amplitude n sub z. The equations for all these quantities are written here, and you see that the field, both counter-propagating waves are excited by the polarization. The polarization at the same time are excited by the field multiplied by the slow varying inversion or by the population inversion gradient. And for both components of the inversion, we have this kind of nonlinear equations. So what we need is to solve these equations, taking into account boundary conditions. That means that the ratio of fields on the left and right mirrors are given. So to solve these equations, we can find amplitudes of polarization waves in this way, then put this amplitude of polarization in the last two equations for the slow varying inversion and population inversion gradient, find dependence of the both quantities on the intensities of counter-propagating waves, and then put all these quantities in the equations for the electromagnetic waves. So we come to this couple of nonlinear equations for these intensities, and they are written for the normalized intensities and using the normalized length along the cavity. This is all real valued because we put imaginary unity in the proper place, so the solution is real value. And to solve these equations, we may introduce the ratio or the difference of these counter-propagating intensities of counter-propagating waves to the sum of these intensities. We see that the derivative of this difference is also positive, so that this quantity Q increases along the cavity, and boundary conditions may be rewritten in the form for this quantity Q. And from this already we find that there is some point inside the laser which we marked by Zm, where the quantity Q is equal 0, so that the intensities of counter-propagating waves are equal to each other, and the inversion, both components of the inversion, slow varying and gradient, has a maximum at this point. To find a final solution, we can rewrite the equation for the value Q squared. It depends on the quantity U, that is the sum of intensities. Find its exact solution. It's quite simple. And then substitute this solution, for example, the quantity V, difference of these intensities, to the equation of the sum of intensities. And this becomes simple equation for U dependent on Z. Finally, we come to this quite long but very simple expression for the relation between this quantity U, sum of intensities, as a function of coordinate along the cavity. This is monotonical function f from U, and depending on the side of the cavity, left to the point Zm and right to the point Zm, we find that we have symmetric solution, but this point Zm is situated not in the center of the cavity, but closer, more close to the mirror with higher reflection rate, higher reflection factor. And to find this situation or this point, we have calculated the distance from this point to we may calculate the distance from the point to the left and to the right mirror, L1 and L2, where L is the distance measured in the cooperative length. And the sum of these two distance should be exactly equal to the length of the cavity. From this equation, we can find the quantity U naught in the point Zm. And after that, we have the complete solution of this structure. So let me show this structure on the pictures. For example, here you see for some parameters of the laser, you see that we have green here curve is the profile of the slower varying population inversion at the left side of the cavity. A yellow curve 2 is the profile of the population inversion gradient. 3 and 4 curves, brown and blue, are the amplitudes of the counter-propagation polarization waves, and 5 and 6 curves are the profiles of the electromagnetic fields. The curve 5 describes the amplitude of the electromagnetic wave propagation to the right and 6 to the left. And you see that this amplitude profiles are not very simple because population inversion grating introduced very strong reflections of these electromagnetic waves. And this is not only Bragg reflections, but it also contains amplification in almost periodic structure. So it's quite, in a sense, it's quite complicated structure.
It's including questions.
Okay, thank you. And so when we have this structure, we can analyze its dependence on the parameters of the laser: length, pumping rate, reflection factors of mirrors. And we do this, for example, from the length, this structure almost does not depend, and the asymmetry factor of asymmetric lasing increases almost proportional to the length of the laser. For example, here you see for some parameters of the laser, when the reflection factors differ in 20%, that depending on the pumping, we have with increasing of the pumping, we have more and more pronounced peaks of this population inversion grating and slow varying inversion, and increasing with increasing of the pumping, we have a strong increasing of this asymmetry lasing factor from almost 2 for the low pumping up to 12 at higher pumping, and up to 100 at more high factor. So you see that 2 orders of magnitude asymmetry will appear due to this population inversion grating. Of course, if the pumping is high enough, and also like in this case, the length of laser become high enough, so we are too above the lasing threshold, this super asymmetric steady state become unstable. But it's another story, and it will be another talk devoted to this problem. You can see that depending on this pumping and depending on the difference between reflection factors, for example, here we have almost 2 times difference, and in the down 2 pictures, we have not so strong difference of reflection factors, but you see that if the pumping is small again, we have only 10% increase of the asymmetry with relation to the initial mode of the cavity. But for the utmost pumping, we have again 100 increase of this asymmetry. So also, if the difference between the reflection factors is quite small, for example, here you see 10% difference, then depending on the pumping, again, you see that the structure of this population inversion grating becomes more and more pronounced with increasing of pumping. And for example, here you can see that if the difference between the reflection factors is quite strong, 5 times here difference, then the peaks of this population inversion grating becomes very, very close to the high reflecting mirror, but still the all profiles becomes the same. If we do above the threshold lasing, there will appear self-modulation of symmetric structure, but the structure itself cannot may also exist. It becomes only oscillating inside the cavity, but still may be conserved. But it will be another talk tomorrow, where I will describe what will happen above this second threshold when this steady state solutions become unstable. So my conclusions are the following. First, we find analytically the solution of steady state superradiant lasing in a local, slightly asymmetric fabric Pirog cavity, which is valid for any kind of lasers. this steady state exists due to strongly due to self-consistent half-wavelength population inversion gradient, which is efficient if a polarization lifetime, that's the phase relaxation time of active centers, is greater than a photon lifetime in a cavity. So in a sense, it's this kind of structure is typical for the super radiant lasers of class C and D, and not very weak, and it is very weakly pronounced for the standard lasers. So that is why it wasn't discussed earlier. We find dependence of this structure on different parameters, and the general outcome of this analysis is that in a very wide range of parameters, the nonlinear single-mode superradiant state, which we found, makes it possible to obtain practically unidirectional monochromatic radiation without the use of well-reflecting mirrors. And the width of this radiation will be, the spectral width of this emission will be defined by the width of the two-level transition level transition, which is used for lasing. And finally, in a super-radiant laser, in the limiting case when the difference between reflection factors is much smaller than the sum of both reflection factors, an instability is expected even in the vicinity of the lasing threshold. That is, even if we're not so above the lasing threshold. I will explain it in the talk tomorrow, but what is important that nevertheless, the predicted strongly asymmetric dissipative superradiant state exists, but becomes self-modulated. And this self-modulation manifests itself as a novel kind of dissipative phase state of superradiant-like base state in the ensemble of active centers with very slow relaxation of oscillating dipole moments. Thank you for your attention.
Okay, yeah, thank you, Vladimir, for this interesting presentation about the case of an asymmetric cavity. Is there a question? Yeah, I see one. Petar, you have a question.
I think that was a clap.
Sorry?
I think that was a clap reaction.
I don't.
It was not a raised hand. Okay, sorry.
Right.
Yeah, so I have a short question actually in point 6 of your conclusions. You on the last slide you have, I mean, you have this criterion and this limiting case there. If you just, I mean, you had some examples for different configurations of R1 and R2 in your presentation. So I was wondering if we go to very high reflectivities that are slightly different, you will always have this instability. Is that an interesting region there at very high reflectivities?
No, for the very high reflectivities, we will come to the situation when the photon lifetime in the cavity becomes greater than the polarization lifetime. And in this case, the correlation inversion gradient will not appear. So we can't consider very high reflectivity limit.
Okay. Okay, good. Thank you. I think we have to move on. Thank you, Vladimir, again. Thank you. Yeah, the next speaker is Vente Liao. Hi, Vente.
Hi, Rob.
And from Taiwan. You're in Taiwan right now?
Yes.
Okay, it's
I'm in Vilnius.
Sorry?
I am in Vilnius.
Okay.
Yeah.
Okay, I see. Okay, good. Then, yeah, so you can share your screen already.
Yeah, sure. Just a moment. Can you see it?
Yeah. So we are now coming to something completely different. It's gravitationally sensitive structured X-ray optics using nuclear resonances. That sounds quite intriguing. So we're looking forward to your presentation, Mente. Go ahead.
Yeah, thanks. So can you hear me properly?
Yes.
Yes.
Okay, good. Okay, thank you. And also my mouse. Okay. I would like to thank Olga for your always kind invitation, and also thanks for sending me this wonderful photo we took in PQE this year. Yeah, and also I would like to thank my student Xinyu Li and my friend Sven Arons for their wonderful contribution to this work. Yeah, and please let me remind you what the gravitational redshift is briefly. So imagine photon has mass equals to h bar omega divided by c squared. So when a photon traveling along the gravity, it will experience a frequency loss, and this amount of change in frequency will goes to gravitational energy, potential energy, like this. So this is a frequency energy change, and this is the so to say photon mass, and g is the gravitational acceleration, and g is attitude change. So it's mg z, like this. And therefore we have this simple formula to describe the fraction of frequency change when photon traveling through the gravity. So it's called a gravitational redshift. Okay, and the idea to measure this gravitational redshift is basically using a high-Q resonator, like this green line, yellow line shows, which is on resonance with this photon traveling along the gravity, and their resonance at some certain attitude, for example here, but they are of resonance at different attitudes, for example here. So you can see the shift like this. So one could measure, for example, the absorption and see if there's any attitude-dependent effect. Then we can see this effect. And in history, this gravitational redshift was observed by in 1960s in Pan-Repka experiment. They use this experiment was done in Jefferson Lab in Harvard University. I showed here in the photo. And the altitude, the height of the building is something like 22.5 meters. And they used, at that time, the just invented Mossbauer spectroscopy to see this effect. Basically, they put a radioactive source on the ground floor. This is a copper-57, and put a nuclear target, iron-57, on the top floor. And they can see the difference in absorption, and they calculate the change, and it's really fit the prediction of gravitational redshift. So I think this is first time people observe this on Earth. Yeah, it's very wonderful. And of course, this is always of general interest to see this effect on Earth. And question is, can we see this in a even shorter length scale? The answer is yes. Yeah, in David Byron's group, they compare the tick rate of two aluminum plus optical clock with an attitude change of 33 centimeters, and they can nicely observe the change in frequency. Yeah, this was done in 2010. Yeah. And yesterday we learned from Junior's very wonderful talk about they use their very advanced Strong-Dian clock in 1D lattice, basically showed here. They can resolve this gravitational redshift in sub-millimeter length scale. So yeah, this is very wonderful. Yeah, and inspired by a very nice proposal of single excitation Dicke state by Manscali, and also the realization of this state in nuclear system by Ralph, Sven, and me study. the gravity effect in this single photon super radiance system. Yeah, the idea was following. For any gradient perturbation shown here to a target, yeah, in principle, when a photon propagates through this perturbed system, its index of refraction also has a gradient along this gradient direction. Therefore, the photon will get diffracted. Yeah, and we replace this perturbation with a gravitational redshift. So basically, imagine in the target, there are many nucleus, and each of them have different attitudes. So intrinsically, there's a redshift already in the system. Therefore, when a single photon absorbed by this system, it will create this single photon Dicke state, single excitation among many nucleus, but we don't know which one. And in the end, they will get a phase gradient along the gravity direction. Therefore, when photons stay in the target longer, it will be diffracted with a larger diffraction angle. And we calculate this effect with different isotopes, and we see indeed, for longer coherence time, we can get a larger diffraction angle. Yeah, this was done in 2015. Yeah, and in fact, Igor Pikovsky also point out this could cause intrinsic gravitational decoherence. Yeah, this is also very nice. Yeah, and today we would like to explore the gravitational effect in nuclear scattering of X-ray further by the following idea. Yeah, let me first introduce the derivation, because the design of system really comes from the theory. Yeah, so when the X-ray propagates through a resonant nuclei, we have to in the perturbation regime, namely most of the propagation stay in the ground state of the nuclei. Therefore, we can solve these two coupled equations. And the first one is describe the time evolution of the coherence between two states. Here, the gamma is a spontaneous decay rate of excited state, and the detuning is the frequency difference between the X-ray and the nuclear transition energy. And P dot E divided by H bar, just the Rabi frequency. Yeah. And also, we have to describe the wave propagation. Yeah, and there are few terms I can explain. On the left-hand side, this is a propagation, and this term describes the diffraction. Okay. And this term describes the electronic dispersion. Yeah, and this term describes the nuclear dispersion, basically from here. Okay, and the electron dispersion is quantified by the index of refraction, the NE, which is in this form, and one can look up their values for different materials in many databases. Some of this one. Okay, and here's the derivation I want to share with you. First, we solve the steady state solution of this one, and we got basically the Lorentzian absorption around the resonance frequency. So this gives the acceptance window, which you can see the X-rays. Okay, and we plug this low EG steady state solution into the wave equation, and we also negate this time derivative and see the steady state solution again. Then we got these one equations, and people call it optical Schrödinger equations because, as you can see, the time is replaced by y, the propagation direction. Yeah, and this diffraction term plays the role of kinetic energy, and also the rest simply just potential energy. Yeah, so this is the optical Schrödinger equation we will use in the following. So the rest of problem is just how to engineer this term to achieve some specific purpose. Yeah, and also inspired by Ralph's another wonderful work to see this collective strong covering in the nuclear optical lattice. They can see the strong covering with this periodic structure. And today we would also like to use this kind of periodic structure to do something. Yeah, I can explain here. Here we design a structured waveguide system. In the middle, you see this green yellow. Green yellow is the periodic structure of some nucleus, which is sandwiched by, for example, the platinum material. And this system, compared to the potential energy we just derived, we will see that we will get a finite square wave I showed here. Yeah, and this finite square wave is given by the platinum. Yeah, and therefore in the middle we have some eigenstates. For example, the red one is a ground state described by cosine function in the transverse coordinate, and it also has many eigenstates. For example, the first exact state described by sine. Yeah, like this. And we would like to see when X-ray propagate with certain transverse profile will get excited. For example, from the red one, when it propagates, it will go into the blue one. It maybe goes back, become kind of a Rabi cycle. And to have this coupling between two modes, we need to introduce some driving terms. So here we look at the second term of the potential. We see there might be a possibility to give a modulation of nuclear density to get this driving. So this is the idea.
So Bente, 5 minutes, including questions.
Okay, oh, no problem. Thank you. Yeah, and we immediately get an effective Hamiltonian with V plus D times a sinusoidal function. So V is a finite square wave, D is a driving. Yeah, given by the nuclear density modulation, and we can calculate also an effective Rabi frequency. Yeah, we get this term. And this gives some possibility of controls by changing the detuning. And this can be introduced by, for example, the double shift, hyperfine splitting, or also gravitational redshift. And we use some parameters. And we really see Rabi cycles when X-ray propagate into the median, into the waveguide. So you see the X-ray enter the waveguide here, and it got splitted. And it's converted and in the end of the waveguide. And we also calculate the fidelity. We'll also see the nice Rabi cycles in the waveguide. Okay, and now I can say something about gravity. Yeah, we replace the detuning with gravitational redshift. Therefore, we can replace the frequency axis with attitude axis. Yeah, and we see the Rabi frequency is proportional to the real part of this rho EG. Yeah, and therefore we can define 4 attitudes at maximum Rabi frequency. Basically, this is the characteristic attitude change, which you can see the significant change of Rabi frequency. Yeah. Okay. Then we use a specific example of scandium 45 isotope. We really can see different diffraction pattern at output in the attitude change about, let's say, 1 millimeter. Yeah. Okay. Okay. Well, and we also calculate this attitude change for different isotopes. We see the scandium is here, which gives you the something like millimeter, and thorium also here give like something like sub-millimeter. And also there are some other possibilities to give the microns. So with this, I come to the end and hope I can convince you that X-ray and nuclear could be a tiny probe of Earth's gravity. And also the waveguide I show you is already an application of gravity. So with this, I would like to thank you. Yeah. And looking forward to your questions. Thanks.
Yeah, thank you, Bente, for this interesting presentation. Yeah, that's really a continuation of your earlier work on nuclear resonance and gravity, right?
And also inspired by your many beautiful works.
Okay, thanks. Yeah, are there questions? Please raise your hand so that I can see you. There's Now Petar has a question, right?
Yeah, so that's a real raise hand this time. So thanks for the talk, Winter. It's
Thank you.
very interesting. Just one question is that you said, so this is all done steady state.
Right.
But at like a synchrotron or something, obviously we have ultra short pulses.
Yeah.
So can you still model this as steady state, or is this something that might require something like XFEL?
Okay. Definitely. You can see basically the steady state gives you the result for certain frequency, single color, basically. Yeah. But we can do something like Fourier transformation. Sorry, inverse Fourier transformation to see the pattern.
I see. So then you'll get the whole frequency spectrum from this.
Right. Thank you.
Okay. Thanks.
Yeah. Welcome.
Okay. There's one more question by Rustem Shakmuratov.
Yeah. Bente, thank you for the very interesting talk. Could you show almost the last slide where you show the dependence of the redshift, gravitational shift with distance for different isotopes?
Right. Sorry.
This is this one, conclusion. Well, as I understood, for iron 57, it's about several kilometers. Is it so? Am I right?
Right.
Okay, thank you.
Yeah, welcome.
Okay, other questions? I don't see. Just have a short question. I mean, on the other end, there's rhodium 103.
All right.
So with this isotope, you should be sensitive even to gravitational waves, right?
Yes.
Yeah. So
you'd be crazy. Yeah.
And maybe this is then your next presentation on the next.
I hope so.
Sorry, quick question. What's the energy of rhodium 103?
It's 39 keV.
Okay.
Yeah.
Bad.
But the resonance is utterly narrow, as you can see here.
Right.
Okay. Anyway, so thanks again for this inspiring talk, Wente.
Thank you.
And we are moving on to the next speaker, who is Dr. Radionichev, also from Nizhny Novgorod. So please start sharing your screen.
Wait, just a moment. Can you see my screen?
Yes. And then it's full screen mode. Yeah. So please go ahead.
How is my internet connection? Can I see my screen?
Yes.
Okay. Can I start?
Yes, please go ahead.
Okay, thank you. Good morning, good afternoon, good evening to everyone. In this talk, in this presentation, I try to describe as briefly as I can our proposed technique of obtaining single photon radiation in hot X-ray range from mesobarial sources with widely controllable temporal characteristics. In the optical domain, in the optical range, there are several methods to shape pulses and to control their characteristics. But in the hard X-ray domain, as far as I know, there are there are not implementations. There are not any implementations of full of on-demand shaping of X-ray photons, and we just propose one option, maybe. So just as introduction, short introduction, I would like to mention that presently there are two basic sources of photon pulses, of single photon pulses in the hard X-ray range. As an example, I am presenting the traditional photon wavelengths, 14 kilo electron volts, and as for radiation pulses from synchrotrons, the pulses are very short and have enormous bandwidths. And even after monochromatization, they are very broad, and the techniques to control the shape, the duration, the interval between such pulses are very limited. Another type of sources are radioactive, Mesbauer radioactive sources. As an example, I present here also traditional source of cobalt-57 and gallium-67. And this type of sources are characterized by very long, relatively long single photon pulses. They can be naturally in different waveforms, but they are quite long. And in this case, there are several methods to control, to transform such waveforms into short pulses and mostly into short pulses. I should mention an effective one of efficient method of magnetic field reversal, but I skip now this method, and I will focus on the Doppler modulation. Doppler modulation of quantum transition energy of nucleus via displacement of absorber or radioactive source. This method of vibration of stainless steel, of harmonic vibration, enables us to transform exponential waveform of the emitted photon into sequence of pulses, but pulse distance and pulse duration are locked to each other, are matched, and the control is quite challenging. There is another efficient type of transforming initial exponential waveform of, for example, 14 eV photon into pulse, into single pulse, or maybe several pulses, via stepwise shift of the absorber, or, like in this case, or the source, radioactive source. The peculiarity of this technique, and this is this similar technique implemented in gallium-67 source. the main peculiarity of this technique is that the shift is rapid stepwise, and then it stops. It stops either when the target or source is shifted by half of lambda of emitted photon, or maybe more than half of lambda. And the peculiarity of this technique is that if one shifts the target or source on lambda half of lambda, the pulse length and pulse shape is determined by relaxation of polarization, of nuclear polarization. But if one shifts absorber or source larger than half of lambda, pulse shape is also can be determined by characteristics of displacement. And the mechanism of such burst is also well known and transparent and nice, beautiful. The mechanism is that if one shift target or source by lambda by half of lambda, the destructive interference between the incident field and incident photon and coherently forward scattered field of nuclear polarization becomes constructive instead of destructive, and the burst is appearing. And we propose some extension, some expanding of this mechanism. Our proposal is the following: we propose fast shifting and return the absorber or the source to its initial position, and there are only two conditions for this technique. The first condition is that the time of such a reciprocating movement, the displacement of the absorber, in this case of the absorber, is much shorter than such a combination of the absorber characteristics. This condition is quite realistic and rather it is not difficult to be implemented. And another condition is just more simple and relaxing, is the amplitude of such reciprocating displacement is less of lambda wavelength of the photon, of the single photon. And and what is the result? And the result of such simple technique is displayed here. It is by this technique we can produce single photon wave packet in the form of variable number of short bursts, including single burst. we can individually adjust the peak intensity of each burst in the sequence. We can individually adjust the duration of each burst. We can adjust individual time interval between the adjacent bursts. And finally, we can produce on demand the individual shape of each burst in the sequence. And now I will show you our calculations, our results. This on the left is the comparison between the stepwise shift of the absorber resulting in gamma echo, well-known effect. And this is the reciprocating motion of the absorber, the same absorber, with the same time of forward motion and the same time of backward motion. And we can see that in the first case, in the case of gamma echo, we have quite long pulse, single photon pulse, and in the second case we have very much shorter pulse, and this pulse is actually maps the motion law, the displacement function of the absorber, and this is verified by this picture. What can we see? We see that, and the mechanism of such bursts are also very. The mechanism is also very simple. It's essentially simple as the mechanism of gamma echo. When in this case, for example, we have a reciprocating shift displacement by half of lambda. When we shift the absorber backward or forward by half of lambda, the destructive interference of forward scattered field and incident field becomes from shifts from destructive to constructive, and then when we displace the absorber backward, we enforce the interference to change from constructive to destructive one. And
it's 5 minutes, including questions.
Okay. As a result, okay. And the result is that the pulse starts when we start to shift the absorber, and the pulse stops when the absorber is returned to its original position. And just 2 slides. So by this kind of displacement of absorber, we can produce, in fact, arbitrary sequences of pulses, of bunches of pulses, of single pulses, of double pulses, with various distances between them, and with various amplitudes also. Amplitudes of the produced pulses is controlled by amplitude of shift of the absorber displacement, and this is one of the example. And the last slide is demonstrating the control of pulse shape, of single pulse shape, amplitude, shape, and amplitude of pulse. We can produce almost arbitrary shapes of single photon pulses by wearing via engineering appropriate displacement function of the absorber and appropriate form of the displacement function and amplitude of the displacement. Thank you for your attention.
Okay, yeah, thank you very much for this interesting presentation about your approach to pulse control of nuclear resonant scattering. That was quite interesting. Are there questions? Yeah, Rustem has a question.
Yeah, thank you very much, Jenny, for this nice talk. I have only one question. What is so special about this example where you impose lambda over 4 displacement? What is the gain about? Because I understand the displacement of lambda over 2, half of the wavelength, but when it is quarter, what do you reach? Why the pulses develop anyway?
The pulse is developing due to, as usual, due to constructive interference between the forward scattered field and the field of the incident photon. When we shift at the distance smaller than half wavelength, the interference becomes constructive, but it doesn't reach its maximum of constructive interference.
Okay.
As a result, the pulse does not is not so high as it would be in the case of half of lambda. And when we return the absorber to its initial position, we enforce to change the constructive interference to destructive one, and the pulse stops. So its amplitude is smaller than amplitude in the case of half of lambda shift.
So I understand that it gives extra opportunity to make more engineering of the shape of the pulse compared to the lambda.
Yes, yeah.
Okay, thank you.
Yes, thank you. And this is just an example of this opportunity.
Okay.
Okay, are there other questions? Then I have one, and you have also this example of zinc 67 on your slides. And is there, what was the motivation to have zinc as an example?
Just yes, zinc. I have no time to talk about zinc, but in our paper, which will be published, which will be submitted very soon, we discuss this case quite detailed, and the difficulty is that in gallium 67, one can, I don't know exactly how to organize, to implement the heralded emission of the photon of 93 keV. But following these experiments, we can implement experiments with just without looking to some heralding photon, and to obtain just similar train of pulses from quasi-continuous flow of 93 keV photons from gallium 67.
Okay, good. Yeah, thank you. And thanks again for the interesting presentation. So we need to move on to the next speaker in this session, which is Petar Andrejic from Erlangen-Nuremberg, not far away from Jena, actually. And yeah, you please, Petar, start to share your screen. So then you have the stage, actually.
This is working?
We deal with Mössbauer nuclei. Yeah, it's presenting well.
Okay. And is my mouse visible?
Yeah, it's visible. Mm-hmm.
Okay, excellent. Okay, so thanks for the introduction. So I'm name's Petar. I just finished my PhD of Hadriana Palfin, actually visiting her in Würzburg right now. So I'm going to present some work we did in collaboration with Leon Losse at DESY on doing waveguide QED of Mössbauer nuclei. So our group's interest is in X-ray quantum optics. So this is using resonant nuclei for the coherent control of X-rays. And our long-term goal is just what novel devices for the quantum control of X-rays can we come up with? And the reason why Mössbauer nuclei are so interesting for quantum optics is first that they're incredibly clean systems. So the Mössbauer effect means we don't have Doppler broadening to worry about. And the natural line width is, of course, incredibly narrow. These are nuclear transitions. And also the long lifetime means we have access to things like time spectrometry. And now it's been quite well established that collective effects play a large role. For example, superradiance or collective Rabi oscillations, which in the X-ray field is more commonly called the dynamical beat. And as the main two sort of systems that have experimentally been well studied are these bulk foil forward scattering or grazing incidence thin film. So to begin with grazing incidence, we form a SLAB waveguide from alternating layers of high and low atomic number. So we have some high atomic number like platinum, molybdenum, to act like a mirror. And in the middle, you place a sandwich just of some as low Z filler as you can possibly get away with. You place a thin layer of nuclei, and this couples in the transverse direction, sort of like a point particle. And you drive this at grazing incidence. You have an approximate translational symmetry, well-collimated synchrotron beams. So you can model everything in terms of your essentially a single plane wave mode, and you get single mode Dicker superradiance. And so here I've included a plot from Ralph's group where they nicely demonstrated the both the Lamb shift and also in this paper, and they also demonstrated the coherent speed up of the radiance from this Dicker mode superradiance. Now, on the other hand, we have unstructured bulk foil targets where what we observe instead of a single mode superradiance, we observe this characteristic dynamical beat that comes from the radiation at the front and back being emitted with different time delays and eventually leading to an interference pattern. Now we have a large optical depth, and importantly, we have broken translational symmetry. So the forward incident wave vector is not preserved, and this is visible in terms of this dynamical beat. and what we observe is initial superradiant decay, but then these oscillations further on. Now, what's been a bit less explored for due to experimental challenges is the waveguide propagation, direct waveguide excitation in these thin film nanolayers. So it's the exact same sort of system as grazing incidence, but the boundary conditions are far more like forward scattering. In particular, we're breaking that translational symmetry. So we should expect to see some of these effects like dynamical beats, etc. So outline is I'll give an overview of the differences in exciting these thin films from grazing versus forward incidence. I'll talk about that theoretical model we developed to describe these. I'll give some examples and the outlook. The first, grazing incidence, as I mentioned before, we create this sort of like a almost Fabry-Perot. If you view it from the side, you can view it sort of like a Fabry-Perot cavity. And you can see the resonances in terms of so-called rocking curves. So you just plot reflectivity as a function of angle. There's some narrow resonances. And these actually correspond to what would be driven from the front would be guided modes of the sandwich. Now, there is an experimental trade-off to be made, which is that you would like to have thicker capping layers and get better local field confinement, so a stronger self-interaction of this collective mode. But of course, as you make your capping layers thicker, you attenuate your driving field more, so you have weaker in and out coupling. But of course, if we come at the front, everything's completely open, and this should not be a problem at all. So we can optimize purely for confinement. So now, as I mentioned before, we've got a different boundary condition, and so we have different propagation characteristics. We're not driving a single mode anymore. Instead, we actually have to consider explicitly the spatial propagation and the coupling to the different modes of the waveguide. So just first, I'll introduce the geometry a little bit. Z is going to be the direction that we stack our layers, and we propagate along X. Now we ignore the Y direction because we have well-collimated beams, and so everything is uniform in that direction. So we have an effectively two-dimensional problem. And as you can see in grazing incidence, we also have to specify our angle of incidence. While at front coupling, we just come in with a plane wave from the front. So to describe these, we used a fully quantized description of the waveguide field that uses the classical Green's function of the corresponding macroscopic Maxwell equations. Now, this is because, at least in current experimental regimes, the electronic scattering is linear. We can describe it just with refractive index. And what's particularly nice is that the Green's function for such waveguides are analytically known and easily solved for. The nuclear response, we're still considering synchrotron experiments, so everything's linear, and we can just use the appropriate linear susceptibility. For the purposes of this talk, we're not too interested in hyperfine interaction, so we'll just take it to be a two-level system. And of course, as I mentioned before, we can obtain everything in terms of the classical Green's function, which will contain all the information on our modes, propagation constants. We can also use it to propagate our input fields. So the mode structures are visible in terms of the Fourier transform Green's function, in terms of its complex structure in the complex wave vector plane. So we have poles, which correspond to guided and leaky modes. Now, these leaky modes, they are modes which are sort of a asymptotic expansion for the near field. They're sort of resonances of the radiative part, which is visible as a branch cut. Now, for realistic materials, we've explored this and found that these leaky and radiative modes aren't too important. We end up being very broadband compared to the guided modes. And so you can just consider them as contributing to the sort of single particle decay rates. And here's a view of the guided modes. Now, of course, these aren't going to be exactly sine and cosine because we have a open velocity waveguide rather than perfect mirrors, but you can see, and also our iron layer has a significant effect, especially on these this lowest order mode. But we can see we can engineer the modes to couple to our layer at different strengths. So for example, this orange mode is vanishing towards the layer center, will couple very weakly, and this is an example of a realistically attainable two-mode cavity. So first, what do these solutions look like? The simplest is, of course, taking a single mode cavity, and we can do this just by making the cavity sufficiently thin to adjust to go below the cutoff. And turns out we can actually transform then for single mode equations to be exactly the same as nuclear forward scattering. The only difference now is that our optical depth is modified by our local guided mode factors. And we also need to include the effect of the overall guided mode wave vector and attenuation in the overall envelope out front. Now, compared to doing bulk foil forward scattering, we do have a much optically thinner sample. So it turns out that compared to just taking, shining a that forward incident mode, this single waveguide mode it greatly reduces your optical depth. But on the other hand, our attenuation lengths are very long because the bulk of this guided mode lives, of course, in the less attenuating core rather than living in bulk iron, which is quite severely attenuating. So it's possible to achieve even up to about centimeter scale attenuation lengths. So on balance, in terms of total optical depths achievable with an attenuation, it's about similar orders of magnitude. But what we get with the waveguides is now we get multiple guided modes. Now, at synchrotrons, of course, we can't really have multiple beams. It's the passive optics are quite challenging. So we just get the single beam almost like a plane wave input. But now in our guided mode, we're going to drive a superposition of all of these different supportive guided modes. And the wave vectors for these guided modes are actually quite close together, which means that the interference between them happens on quite a long scale. So practically speaking, we can see we get tens of microns of attenuation lengths. Now, this is a length that is practical to engineer the x-axis geometry of our sample to take advantage of this interference and do something like the analog of an optical lattice. So you can see here is an example of the interfering scattered field of a thin strip of resonant nuclei. So first, in the bulk, if we just consider a bulk unstructured layer in a two-mode waveguide, we can first see what happens to the forward scattering spectrum. So here we can see a sort of 2D plot of intensity with both time and also the spatial position along the waveguide. So varying the length of the waveguide, essentially. And you can see it's quite similar, but of course has these characteristic beats, which comes from this two-mode interference. And this is also visible temporarily because although these beats are gradually compressed together as time goes on, if we start close to one of these interference minima, you can still see in the time spectrum this effect like having a skipped beat and so forth. But perhaps more interesting is to now actually exploit this spatial structure. So in a grazing incidence, this X, we can structure different layers along Z, but along X, because we have this single wave vector, not much interesting happens. You still just get the same single mode superradiance. Now with this two-mode interference, this structure in the X direction is important. So let's consider chopping up this layer into little strips, as we should see to the right. And if we make these strips sufficiently small, we can make them small, thin compared to the wavelength of the interference beat. And we can also treat these as being excited by a single Dicker mode, which makes this problem essentially like discrete and the analog of something like an atomic array. So as an example, here's the two-dimensional field profile on resonance. So you can see the difference between placing the strips at the beat wavelength apart or placing them at a half wavelength. So at the beat wavelength, each strip sees the full in-phase field of its previous neighbor, and they all interfered constructively, while placing them at a half wavelength, they split into two. In the ideal case, two non-interacting subensembles, because everything in the even position sees only the interference minima from the odd positions, and the fields don't construct very strongly at all. So the result is actually that the optical depth of the right-hand side is only half of what you expect for the total thickness of the strips present. And this also has an interesting sensitivity to the total number of strips, because you have effectively these two non-interacting ensembles, and their transmission can easily be shown just to be, at least in the ideal case, they just take the individual transmissions to the power of the number of strips. In the case of an odd number of strips, one of these two ensembles has an additional strip compared to the other, and it will, as a result, have a different time spectrum, and more specifically, a different interference beat time. And this can be visible. This is actually in the non-ideal case. Even in the non-ideal case, this can be visible by shifting our observation point relative to the final strip. Because everything's periodic, it only cares about the relative period to the interference beat. And what you can see is that as you have an even number of subensembles, you don't shift this dynamical beat very much, but we have an odd subensemble, you can actually see a measurable shift of the dynamical beat with respect to your proper observation position. So the outlook is that we've been able to show that good quality most power waveguides are possible for realistic materials and layer structures, and Leon has actually successfully measured the single mode dynamics, and he's preparing an article at the moment. I would say, from my point of view, the next experimental step is to verify multi-mode dynamics, although Leon tells me he's got a beam time next weekend to look at a slightly different problem, which is the forward scattered spectrum from a grazing incidence-driven system. And from our point of view on the theory, we would actually like to structure the layers far more than just, strips in the X direction. In particular, we're hoping that if we structure more in the Z and Y direction, we can have bidirectional coupling, at least with respect to that direction, and we can do things like implement hopping models or 2D lattices, but with X-rays. So with that, thank you for your attention. And if you're interested in our preprint, here is the archive link.
Yeah, thank you very much, Petar, for this interesting and inspiring talk with the new perspectives for things to be done. Yeah, are there questions? Yeah, I see one by Rustam. Please.
Okay, Peter, I have a question about your strip model. The strips of the absorber, and as I understood, the length of each piece of strip and the distance between pieces is about wavelength or half wavelength. Am I right?
Oh no, so the width, it's not the transition wavelength, but it's the interference beat wavelength.
And how this distance is different from the wavelength of the radiation field? What's the
so it comes, if you see here in this 2D, in this complex wave vector plane, it's the inverse of the difference in wave vector in the distance between these in the real part of the Q plane.
Can you just estimate the physical length, not informal?
Physical length. So I mean, this actually you can see here, for example, in this particular case, is about 25 microns.
Okay, it's the size of
it's actually
hundreds of micron. Is it so?
Yeah. So it's tens to hundreds of microns.
Okay,
so, I mean, experimentalists don't like when I suggest this, but you can actually get some incredibly good waveguides using uranium as capping layers. You get things like 100 micron beat lengths and like centimeters of attenuation lengths. But of course, uranium is radioactive, so they don't like that for the for the spotted chambers.
For iron and, for example, platinum, not uranium.
No, actually, this example is molybdenum, because molybdenum we found happens to be one of the nicest capping materials that is non-radioactive. And then iron is the resonant material. So this we don't have as much control over, at least if we want to use a particular transition.
So it's experimentally visible to make these pieces of 10 microns, for example. As I understand.
So this, of course, we haven't done a proposal yet, but I've been talking to the experimental collaborator who prepares the samples, and he's at least confident that you could achieve something like that using photolithography, for example.
Okay, thank you.
Yeah.
Okay, are there further questions? I don't see, so I have the occasion now. So you, Peter, you always had the 1 nanometer iron in the guiding layer.
Yes.
Where's the limit? How thick you can get to be for this this whole game still working before reaching, maybe if you make it thicker, maybe you end up in having 2 coupled cavities or whatever. New scenarios actually. So what is that the 1.0 nanometer the optimum here?
Well, you can see, obviously I haven't numerically optimized this. This was all kind of done by eye, but you can even see here with the modes that 1 is already not fantastic, because you can see that actually this first guided mode has a noticeable dip. So if you as you increase the width, this is going to get lower and lower. So I'd say maybe about 2 microns, not much more than that. That said, of course, this is only because we've just been considering the most sort of simplified, ideal analytically tractable models. If we're going to just be willing to use numerics, there's absolutely nothing wrong with making a thicker model. It's a bit more complicated, because rather than point-like coupling, of course, you have a distribution of excitation across this layer, and then you've got you could have like multiple layer modes to consider as well.
Okay. Yeah, are there further questions? I mean, just a question out of curiosity, maybe you have calculated this as well. If you say just avoid any guiding, if you assume vacuum as a guiding material, guiding layer, yeah. So with a free standing iron layer in the center, in which way, however one realizes this, is that to which results do you come then regarding propagation distance?
So actually, this I didn't do. I know Leon did it, but I honestly can't remember. But I think it was still around centimeters. It basically, at some point, it's just unavoidable that fraction of a mode that is in the capping layer picks up some of that attenuation. Yeah.
Okay. Yeah, I think then we are at the end of the session. So let's thank Petar again and all the speakers of the session for the very interesting and intriguing presentations.
Thank you to Ralph. Thank you for chairing the session. And let me remind you that just in 7 minutes, we have our plenary session. So please stay connected. It is the same link. We have plenary session in 7 minutes. Okay.
Okay. Thank you, Olga. And
thank you.
See you later, right?